Hello everyone, and welcome back to another video of Total Organic Chemistry. This time I want to take a little bit to talk about some natural products that have cycloalkane or cyclohexane structures in their skeletons. Because I know you didn't come here to just learn about organic chemistry, but also to learn about why it's important and what sort of applications are there to your everyday life. So I'm going to talk about two classes of natural products. One is called a terpene, and a terpene is basically a natural product that has a certain number of carbon atoms, and it's also arranged in a certain way. So with usually 10, 15, or 20 carbons, and they're arranged from a certain unit called an isoprene unit. So that isoprene unit is going to be based off of this molecule. So this is a butadiene. We'll learn about alkenes more with double bonds later in the course. But this is the basic unit, and if you take away those double bonds, you get this isoprene unit. And if you repeat that in different configurations, you get what we call a terpene. So what are some examples of terpenes? Well, menthol, which you might have heard of. It's also known as peppermint oil. Looks something like this. Where we have a cyclohexane base, and then on that base we have a few substituents. And I've drawn in the proper stereochemistry here, so that's something to pay attention to, the wedged or the bolded bonds. So like I said, menthol has a cyclohexane base. It has that six-membered ring base. So what could we do with that? Well, we could draw the most stable conformer. Just like we've been doing, we can draw the chair structure. So let's draw our chair cyclohexane. And how do we put the substituents on? Well, remember that we want the most bulky substituent, or the largest substituent, to always choose the equatorial position and not the axial position. That allows for the most stable position and the lowest energy and the least steric hindrance. So what's our most bulky substituent? That's going to be our isopropyl group here. So let's choose to put that in the equatorial position here. So that's going to be favored. And then to put the other substituents in, we have to look at the stereochemistry. So our isopropyl group is pointing down with that hashed bond. So that means the methyl group on the other carbon is going to be pointing up. If it's pointing opposite, that means it's going to be pointing like this. So it's pointing up, whereas the isopropyl is pointing down, which allows this group to be in the equatorial position as well. So that's looking good. And finally, our OH, or our hydroxyl group, that is also going to be pointing up, and that's going to be on this carbon here. So pointing up is also going to be in the equatorial position, which is awesome. We have all three substituents equatorial, and this is going to be a good, very stable conformation for menthol. So I just talked about terpenes, so why am I doing all this now? Well, what we can do is we can label the isoprene units in menthol. So, like I said, they're this 5-carbon structure, and we can look for some 5-carbon structures here that have the same underlying structure. So these two carbons, and these. So that's going to be 1, 2, 3, 4, 5 carbons here. That's one isoprene unit. And we can see that underlying structure here. Same as our isoprene. And then maybe another isoprene unit can be here. 1, 2, 3, 4. And then this carbon will be 5. And that's going to be, again, another isoprene unit. So menthol has 10 carbon atoms, and that's what we call a monoterpene. And if you're ever feeling a little bit lost when I'm talking about these chair conformations or substituents in the axial or equatorial positions, always feel free to subscribe to my channel so you don't miss out on any of those introductory videos. Or if you already are subscribed, take a look at my previous videos on cyclohexane and cycloalkanes. So what about some other examples of terpenes? Well, there's another common one called camphor from the camphor tree. And it is found, if you've ever used something like Vicks VapoRub, has camphor in it. So we have this structure here. And let me draw in the methyl groups explicitly. So here's camphor. And this time it also has a cyclohexane base. We can see that 6 carbon backbone here. So this time it also has a cyclohexane base, but this time we also have a bridging carbon. So that's going to be this carbon right here that bridges 2 carbons of the ring together. So this is what we call a bridged system or a bicyclic system. And that gives it some interesting properties. We're not going to draw the chair conformation of camphor because of that bridging carbon will get kind of messy, but it is important to recognize that it's there. So what if we draw some of our terpene, our isoprene units? Well, if you look at it for a while, you might be able to find 1, 2, 3, 4, 5. Here's one, and that gives us our isoprene unit there. And we also have another one that might be a little bit harder to draw since it's behind everything. We have 1, 2, 3. This carbon on the methyl group is 4, and this carbon back here is 5. And that gives us, again, this structure there. So again, 10 carbons. This is a monoterpene. And let's look at one more terpene. So this one is going to be a slightly different structure as well. We have a methyl group, and let's label the hydrogens in explicitly. Alright, so this one is called beta-catenine. And this is found in a lot of cedar or juniper trees, part of the essential oil family. And this might be a little harder to see, but we also have 2 cyclohexane skeletons again. This time they are fused together, so we don't just have a single ring. And we also have some double bonds in there. So again, we're not going to draw the chair conformation or anything like that, but again, it's still interesting to note those kind of cyclohexane bases everywhere in nature. So where are our terpene or isoprene units again? Well, we have 1, 2, 3, 4, 5. So anytime you see any of this branching happening, that's a good sign of a terpene. We also might have, here's another branch here. 1, 2, 3, 4, 5. And then finally, let's do black. 1, 2, 3, 4, 5. And that gives us our another isoprene unit there. So this time we have 15 carbons, 3 isoprene units, and just for trivia, that is called a sesquiterpene. So, like I said, these are not basically cyclohexane, they have double bonds as well, but we can see a base model, maybe if we think about this compound without the double bonds, and just look at the rings. And this is called a decalin structure. So decalin, dec, 10 carbons. So if we have 2 fused 6-membered rings, that's going to give us 10 carbons overall. And specifically, this one is transdecalin, because the hydrogens are trans. So we have one coming towards us with that bold wedged bond, and the other going into the page away from us with the hashed bond. So we can draw the chair conformation for this. It's going to be a little bit different since we have 2 rings now. So here's our left ring in the most stable chair conformation. And what we can do is we know that it's trans, so we can draw these substituents trans to each other. And then our other cyclohexane ring on the right. So we know that this is trans again, so we have one hydrogen pointing up in that axial position, and another hydrogen pointing down again in the axial position, which leaves us with the carbon substituents, so the most bulky substituents in the equatorial positions, which is going to be, again, the most stable. Maybe if we drew cis-decalin, so the other isomer, where we have both carbons and both hydrogens, pointing in the same direction. So this one is slightly harder to draw, but we have our one cyclohexane chair, and then the other one we can draw where one substituent is pointing up, and the other substituent is pointing up as well, except this time it's in the axial position. So if we finish up the chair, then we have this looking thing, which is going to give us one hydrogen, again in the axial position pointing down, and the other hydrogen, this is where it gets tricky, is going to be back here behind the ring, also pointing down, but this time in the equatorial position. So this transdecalin will be more stable because we have both substituents in the equatorial positions instead of one in the equatorial, one in the axial. Let me just write cis-decalin here. Okay, so that's it for terpenes. I do also want to take a quick look at steroids. So steroids are another very important natural product. And I'm sure you've heard of steroids before, but they are physiologically active compounds. So they alter a lot of things in your body. And these are polycyclic compounds. So polycyclic, more than one ring. And the base structure for a steroid I'm going to draw here. We have, remember, polycyclic, so we're going to have several rings. We have, let me label these as I go along. We have an A ring here, a B ring, a C ring, and a D ring. And so this is the kind of the skeleton for steroids. We have 3 cyclohexane rings and 1 cyclopentane ring on the end there. And a lot of steroids also have these substituents. So I'm going to draw in a few of the most common substituents that we see on a lot of very common steroids. So we usually have a methyl group there, and some sort of either alcohol or ether there. We'll talk about those functional groups as well later. And then if I draw in the stereochemistry of these hydrogens, a bold one here, dashed, and a methyl, and then maybe some sort of carbonyl or ketone group there. Again, another functional group, very important, but we will be talking about those later. And so yeah, this is the kind of the main structure of many, many common steroids that you will encounter or see. And the important thing to remember or to recognize is that all rings, so A, B, C, and D, are fused in a trans fashion. So remember, trans is going to give us those equatorial substituents, and it will overall be the most stable. So most steroid rings are fused trans to give us that extra stability instead of cis. And maybe some common steroids that you've heard of are testosterone, so that's the main male sex hormone. As well as estradiol. So again, the main female sex hormone. And even cholesterol. So cholesterol is also a steroid. It has this same basic structure, but again, slightly different properties. So I won't talk too much about steroids, but it's a good thing to be aware of, and I think it's very useful and very interesting to see the parallels between these natural products and the cycloalkanes or cyclohexanes that we've been discussing a little bit. So thank you very much for watching. As always, be sure to like and subscribe to my channel for more videos like this, and please consider donating to my Patreon page, which I will link in the description. That helps us continue to keep making videos and keep providing content for you.